Hi, I'm Brendan Gorey, and today I'm going to show you temperature predictions using time series in Spark. The topic on which we're going to cover is climate change. So most of you have heard over the past decade and even before then, predictions made about human activity with the increased carbon dioxide levels in the air, in the atmosphere, how that is changing our climate. Different aspects have all pointed to the same conclusion. The acidification of ocean waters, more carbon dioxide in the air, that's making the ocean waters more acidic. We can see difference in tree growth from very old trees to newer trees, looking at the rings dendrology, how that has changed over the climate. We all know about the receding glaciers, which result in rising sea levels. Also, more severe weather events. We've all been made aware of hurricanes, typhoons, floods, and heat waves. But there's also droughts, the famous California drought in the West Coast and in the western part of the United States that's causing a lot of issues, but also polar vortices. And these are very cold pockets of air that will descend farther south than they typically would go during winter months. Regions that don't see very cold temperatures would experience these bitter cold snaps, which is also related to climate change. And then also we unfortunately see species that are unable to adapt to changing climate, while other species are flourishing, ones that enjoy warmer weather, hotter weather, drier weather, whatever the difference is in that specific region. They are adjusting very well to it, and their numbers are increasing. So the climate change just means something different to a particular region within the globe. And that's what we want to explore a little bit more. And we're going to do that by looking at 16 cities in the continental United States. And we chose cities that represent different regions within the country. So we have the hot, dry Southwest and the more temperate, cooler, wetter regions of the Pacific Northwest and the Northeast, as well as warm, humid conditions in the Southeast. The software we're going to be using, all the code will be written in Python. The examples you'll see will be in Jupyter Notebooks. It will run on top of the Spark infrastructure. We're going to download Facebook Prophet as one of the packages and APIs we're going to use for time series analysis. The Python packages, most everyone will have Pandas, Matplotlib, NumPy, and so forth already installed. If not, you just want to double check. Very easy to install, very straightforward to get going with time series. And the operating systems are going to switch between Windows and Ubuntu depending on the technology that we're going to be using. So to download the data, we went to pirateweather.net. This website hosts a lot of data and observations of weather data going back to 1980 for a lot of cities throughout the world. Again, we're just focusing on 16 cities within the United States. And here's a list of those cities. Again, we try to capture all the different types of regions and different climates, microclimates within the United States. It's a very straightforward loop that we have here. We're setting the time frame from 1980 up into 2021. We just wanted a complete year that the website offered. The API requires a longitude, latitude, as well as time frame for which we want to get the weather observations. I went to latlong.net a website that what you have to type in is the city, state, and country or a region. Is going to return back the longitude and latitude coordinates, and then you put that into the API, and the API is going to return a JSON file with 24 entries. Each entry is an hourly observation, and we'll cover what those observations are in each JSON file. Just as a note, I have this commented out because it takes a very long time. Each API call is roughly about a second. And for 41 years, for 16 cities, it took a long time to run. So the code will work. I just have it commented out because it takes so long to run. So let's go ahead and take a look at our Python code here. So as mentioned, we're going to hit the API, which is going to download all of the information that we have. The next thing we do is we're going to combine the JSON files into one large JSON file that's eventually going to be converted to a CSV file for each city. Along the way, we're going to check the integrity of the JSON file. We want to make sure that the data are in the proper tags, and also that we have 24 observations per city per day. Because we're doing an API call and it has to be a constant internet connection, there may be problems with the server or your local machine. There might be a disruption and you get an incomplete file. So we just want to make sure for every download that we have the proper structure of a JSON. Once we do, then we can go ahead and convert that to a CSV file. So we load the JSON to a Spark data frame, and then we can save that data frame as a CSV. Important to note here that there is something, an offset that's in the JSON file. All the times captured are in GMT. But we wanted to standardize the time zones, because when we run a time series, the time zones should be consistent through all the measurements. We just want to make sure there isn't any type of jitter or disalignment with the data that we're showing from the time series. So we're going to standardize everything to EST. It doesn't really matter. It could be GMT, it could be Pacific time. It doesn't matter what time we choose. It just has to be consistent. And also important to note that the downloaded data, the time frame is in Unix, and this isn't very legible timestamp time format. So that's why this weird calculation that is done there. We're going to eventually turn it back to more legible year, month, day, hour, minute timestamp within the CSV file. And also with the CSV file, there's a lot of data that we have here. We're just interested in the location, the timestamp, and the temperature. So we're going to drop all the other columns that are in the CSV file just to help make the models run that much more efficiently. And then we're going to go ahead and save it as a CSV file. And we're going to now try to install Spark TS. This looked like the best API package for time series for Spark. However, we did not have much success installing it. We went right to the GitHub repository. It installed, but it would not import in Python. And then we tried another way of loading PySpark with the dependencies, the jar package for Spark TS. Again, it installed and Jupyter Notebook loaded, but we couldn't import the model library. I think it had something to do with the structure when we did a pip install for the Spark TS and even from the GitHub repository. So whatever your Python library is in the site packages, Spark TS, the models, this is the code that we want to access when we do a from Spark TS import ARIMA, regression ARIMA. This is what we're trying to access. It just unfortunately gave us errors, so we needed to find another approach. But we can go ahead and do a little bit of EDA using our Spark. So we load the large CSV file into Spark. And by running the EDA, we're just going to do some high-level statistics on the data that we have. And we're also going to check to see if there are any null or incomplete values. So the first thing we see is that we have 5.8 million rows with 12 features. And these are the data types for all the features. We saw before that we're dropping the features, so we don't really care about most of them. We do want to make sure that the time is of timestamp and that the temperature is a numeric value. As we said before, we need these specific data types for these models to run. And because we did the clearing of the cleaning of the JSON files, we don't have any null counts or any end values. And here are the statistics that we see here that actually make sense. The standard deviation for Miami and San Francisco are low. And all that is saying is that it's a pretty temperate climate throughout the year. It doesn't have a lot of wild swings from summer to winter. But regions like Minneapolis and Billings, they do have big seasonal changes. It's very hot in the summer and very cold in the winter. So we get those big spreads throughout the year that would increase the standard deviation values. And then we have the minimum and the maximum values for all the regions. Billings has a very big swing, about 147 degrees, you know, both ways of the lowest temperature recorded there in the past 41 years and the highest temperature. Phoenix probably wins with the highest temperature there, and Billings with the lowest temperature. And in terms of the standard deviation, getting back to that, the cities that we would normally associate with spring, winter, fall, summer, that's going to be Chicago, the Boston, New York. They all have, Washington, St. Louis, they all have around the same standard deviation. So that gives us a sense that there is seasonality and that the temperatures do go up and down consistently. So we're just going to use Spark, the data frame, and just run some simple queries on it. And we're going to plot the timeline. And by plotting the timeline, the time series just for 1 year, we chose the last year, we'll see that these plots resemble the standard deviation. And as expected, the edges of the plots, the x-axis here, the colder months, and we have the warmer months in the middle, and temperatures on the y-axis. And we would see temperatures increase and then decrease. And we kind of get a sense, it's been a very cold month, February for Billings in 2021. And again, we see up and go down and up and go down. But if we were to see one of those cities that were pretty temperate, like Miami, we see a pretty flat curve there. And again, that resembles the standard deviation. It was a low value, so we wouldn't expect to see very high, we wouldn't see a camel as much. And here's San Francisco again, with a pretty flat, but we look at Washington, D.C., we have more of that distinct curve. So we can go ahead and try to predict this with the ARIMA models. So the first thing we did was we just chose one city and we're going to take a specific time frame for that one city, and we want to find the best PDQ values for that city. And this is just a simple grid search. It takes all the permutations, we fit the model, and that returns all the combinations of PDQ and the RMSE. And we chose the root mean squared error as the metric for the best ARIMA PDQ, which is 3000 at 1873. And we put that into our Ceramax. We're going to leave the default values here, and we know that it's 365 days. We go ahead and fit it. An hour and 11 minutes. That is just for 2 years for one city to fit the model and run predictions. For the size of the data that we have, this isn't very practical at all. And we can see the model did okay, the L1, L2. We have pretty good p-values here. P-value for L3 could be better. And for these other values here, I chose 365, pretty high p-values. And this probably isn't a good model, and it would have to be tweaked even before we try to run it through all those models. And with an hour and 11 minutes, this isn't so practical. Well, enter profit. So I'm going to switch over to my Ubuntu machine here with Python, Jupyter installed on it as well. And here we are going to import your profit. And it comes with some nice validation tools as well. And we're going to start the process the same way. We're loading in a CSV file, and we're going to define a function here for profit. And we're going to fit the model. And the model here, we're going to say that's a linear growth. Some of the parameters you can find in documentation online. Definitely know that there's yearly seasonality, but we could certainly tweak with this. Weekly seasonality, daily probably would be overkill. And we chose additive seasonality mode to fit the model. Then we're going to rename these columns. It's very specific for profit that it wants to make sure that the Y and DS are the column names for this, for the model, for it to properly run. And then we're going to do future predictions on it. And then we're going to evaluate how well the model runs based on the RMSE, but you see here that profit can create different values of it. And here are the paths that, the plots, excuse me, that come out. And I did that for all 16 cities, all 41 years for 16 cities. That was 3 minutes and 26 seconds. Obviously, a lot better of a method to use than with the slow Ceramax. And the profit just screamed through that data and gave us pretty good measurements. We see that the majority of cities did rise, and the confidence here was high that the trend is going to continue to rise. We see a nice seasonal decomposition that profit gave us. And all these black dots are the observations, and we can see the extreme values over the predicted consistent seasonal values that we have. And I just chose New York. There was a nice plot here that showed all the differences. And each city we see has its own breakdown. And what I thought was interesting was the cities that had downward trend had a very high or very low confidence because it had a high spread. But the cities with increasing temperatures had a pretty thin, you can barely see the confidence shading there for Atlanta. So the profit model is pretty confident in its projections that the next 4 years are going to continue to increase average temperature in Atlanta. And we just wanted to see how accurate was that. And we see the RMSE, we're going to pick on that since we use that for the Ceramax. These values are lower than the values that we had for the Ceramax. The Ceramax was about 18. And for here, there isn't any value close to 18. And even with the worst value, so we did the maximum and the minimum. So even the worst projection that it had, it still was a pretty good prediction. So we learned that Spark TS, even though it was lauded online about a very good solution, unfortunately, we couldn't get it to run either on Windows or Linux. But I think even if we got that to run by using Prophet, it was extremely efficient, and we could run a lot of data through and get some very informed results pretty quickly. I think because of this, we could be using other features in there. What is the precipitation? What is the pressure? What is the wind? These would indicate some extreme weather events. Humidity might be an indication of drought or more rain. There could be other, just in that data set that we downloaded, there could be other measures that we could put into the model and see if we can detect any type of trends in there. So thank you very much for watching. I hope you do try this package and try with some other data sets. And Prophet is a very, very efficient engine running on Spark. And we ran a lot of data through and got some interesting results. Good luck. Thank you.